We have now come to the second lecture of today's program, and it is my absolute pleasure to introduce our next speaker, Professor Sudhakar Panda, a distinguished physicist and a leading authority in quantum field theory, and string cosmology. Born in 1959 in Tente, Orissa, Professor Panda has forged an illustrious career marked by profound contributions to high energy physics and theoretical cosmology. He completed his undergraduate from Utkal University and postgraduate from the Indian Institute of Technology, Kharagpur, followed by a PhD in high energy physics from the Institute of Physics, Bhubaneswar. His academic journey spans postdoctoral research at world renowned institutions, including TIFR, ICTP Italy, and the University of Groningen, Netherlands. Currently, he serves as INSA senior scientist and has held directorial roles at both NISER and the Institute of Physics, Bhubaneswar. With over 75 research publications and multiple honors, including Fellowship of INSA, NASI, and IASC, as well as the J.C. Bose National Fellowship, Professor Panda's work continues to influence both scientific thought and institutional leadership in India. So let us all join in warmly welcoming Professor Sudhakar Panda. Sir, you may take your time.
Right. Thank you very much. I should thank the organizers who are in the physics department of Assam University Silchar for giving or making arrangement for these hundreds years of quantum science. Uh, As you are, you can see me in the framework of Atri Desmukhya, but believe me, I'm not Atri Desmukhya. I'm Sudhakar Panda. And thanks for your introduction. Uh, what I had thought from the beginning is that this is a short course on quantum science. Some people might be getting worried that what is quantum science, because we are all familiar with quantum in the domain of quantum mechanics or quantum field theory. But the way this subject has developed, I feel that now this should go to the curriculum of at least master's degree and PhD degree. If not a regular course, one can offer an elective course so that people know about this. And for me, I've used this in couple of papers like path integral derivation of Langevin equation, Fokker-Planck equation, but and similarly also I've used it in the context of cosmology. But believe me, using it in your research work and teaching a course on that subject are completely two different issues. I have been following a principle in my academic life is that if I believe that I'm ex, an expert in this subject, that idea is wrong. I understand it only when I teach the subject. So I was preparing in that. I was trying to learn open quantum system, and since I want to learn it, I decided that I should talk about it. But many people who are of my age group or little bit below me, they have not understood this subject is not understood by everyone. So I also am trying to see that when I communicate as I understand, you can see that now it is open quantum system, but then people say quantum science because it is being used in chemistry, biology, and many other subjects, which you have, many other fields, which you have already heard about in the last few days. So let me start now without going into much details. Open quantum system is basically describes the dynamics of non-classical evolution. And later on we'll see also it does take care of uh, quantum evolution, but sometimes the evolution changes, uh, and which I will describe. Okay, so they are being used now in quantum optics, quantum information processing, quantum com- computing, etc. As you have many talks on this. I will try to avoid Bob and Alice, which almost all speakers possibly used, and that the way it is. I want to give a picture which makes me, based on my previous knowledge in quantum mechanics, quantum field theory, to understand this. And so I'm asking, are you hearing me? Hello, are you hearing me?
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Okay, thank
Yes,
you.
sir.
Thank you. And the region that we have been studying now, open quantum science, itself says that there is a closed quantum science, right? So, throughout our life, we basically did closed quantum science, and now how to move over from closed quantum science or quantum physics to open quantum physics. Why do you want to go over there? Because in the closed quantum theories, we never bothered about environment. And the environment could naturally influence the system, and it traces its roots from quantum optics and has found its application ranging from condensed matter to quantum cosmology. This open quantum system allows a systematic understanding of corresponding process, understanding of irreversible process, such as decoherence and dissipation. For a correct understanding of realistic quantum dynamics and possible implementations, this is essential for possible developments of quantum technologies, which you heard also like quantum devices, etc. But I will go on totally theoretical way how to develop open quantum system from our knowledge of closed quantum system. Okay? So what I will be speaking will give you a feeling the basic ideas of open quantum system and the tools we need for the same. Uh, you will see that if not possible today, tomorrow, I will use both the traditional master equation as well as the functional or path integral approaches, which you have learned it from your quantum mechanics and quantum field theory, but I will touch upon it because basically everyone in the audience will not be in the same frequency of knowing the subject. So, as I told, once I try to understand more, I am surprised that why it has not gone to the place of college and university curriculum. Specifically, at least in India, I don't know about the other countries. I will try to take tour of known things to you and proceed to show you the regions of learning open quantum system. But before I do this, let's make some remark or recapitulate the motivation for you to learn open quantum systems. You know, the quantum theory of open systems represents an important problems in quantum statistical mechanics. So I will be using some statistical mechanics, quantum statistical mechanics, and quantum mechanics both to go over to open quantum systems. It provides a natural route of, for reconciliation of non-unitary processes like damping and decoherence with the process of quantization, as you will see. One starts with the conservative composite closed systems consisting of the system of interest and take care of its environment to which the standard rules of quantizations are applied. Thus, we'll see that the total system comprising of the system of interest which you want to study and its ambient environment, they both will evolve by unitary evolution, and then the environment coordinates are basically eliminated to give a closed equation, or what I say that we are discussing a reduced dynamics for the dissipative system alone. However, you should remember that in this picture, friction comes by the transformation of energy from the small system, that's our system of interest, to the large environment. Okay? The energy, once we transfer it, disappears to the environment and is not given back within any time of physical relevance back to our system, because the environmental system that we are talking is much bigger than the physical system of interest we are studying. There are many approaches to quantize such a theory of open systems, and the traditional approaches include the master equation and Lagrange equation, etc., which possibly I will come later or day after tomorrow. But in many scenarios, the functional integration, that is path integral approach, provides a practical method of description for us. So that's what I will try to pick up something and tell you. And recently this subject is has got much attention is because of the spectacular progress in manipulation of quantization of quantum systems, quantum states of matter, encoding, transmission, and process processing of quantum information. So that's where everyone is trying to see that how we'll increase our tools to understand the problem of how to control the environmental impact, and then comes the technology side. We have heard about making devices and heard about how to reach quantum operators, but I had planned, along with the organizers, I had planned that my lecture set should be foundation lectures in this subject, and that should have come in the past week. But because of some practical problems I faced in my family front doing this took to come back basically from this week. And by this time, you know lots of things. That's why I saw how the people are giving their talk. So we need to have a proper understanding and control of environmental impact. The usual way we learn quantum mechanics of field theory. So I will now recall quantum statistical mechanics and path integral. Many people also don't know quantum statistical mechanics properly and avoid path integrals because you get there too many number of integrals or product of integrals to be done. Somewhere you have to pay a price between standard quantization rule and path integral approach. So, as you know, the statistical mechanics tries to find out how macro systems emerge from their microscopic origins. Often this requires also the application of laws of quantum physics and hence quantum is called quantum statistical mechanics. Let me recall few facts of quantum mechanics. By the way, if someone has questions, you can ask me immediately. So I'll try to answer. And if I don't know the answer, first thing I learn in academic life is how to say I don't know instead of guessing an answer and give. And I appeal to the younger people, mostly who are doing PhD and postdocs. It is better to say I don't know. And if the second question you ask, and again I don't know the answer, I'll tell that the same answer as the first question. Okay? So I want to be honest with myself and I want to be honest with the people I'm talking to. So let's recall some facts about quantum mechanics. A quantum mechanics system lives the so-called mathematically in a Hilbert space, which I denoted the curly H. This is a complex, complete, complete linear vector space and equipped with a positive semi-definite inner product. So I hope you know already what's an inner product of two vectors. And now in this case, the only thing is that these vectors are candidates in a bigger vector space called Hilbert space. We also sometimes follow Dirac's Bra and Ket relations for representing the basis of states. So psi and psi bra and psi crets are the Hermitian conjugate to each other. So now, let me give an example. We all know that states of a two-level system. And believe me that when the quantum information people were talking about qubit, I was at a loss. What is a qubit now? So this is two-level system called qubit in the quantum information arena, and these are nothing but the following two vectors which I have denoted one by 0, which vector is with components 1, 0, and the other state I have denoted it by 1, which is the vector 0, 1. These are the usual things one does with a two-level system depending on how you are trying to solve the problem. And besides this, a complex linear vector space is a set of elements or vectors which are closed under addition and admit multiplications with complex scalars, but they don't change many properties of this vector space, and that also is linear and associative. Further, there exists a unique zero and identity in the space, vector space, because we should have a starting element as well as we should have an identity element, because if you want to multiply two vectors which are inverse to each other, should give an identity, and that should be contained in this vector space. An important concept in these issues is the notion of an inner product. What is that? Giving two states, psi and phi, say, the inner product is defined by the ket psi multiplied by the state graph. Okay, this should have the vector space should define this, because inner product, as you will see, plays a very crucial role. And a vector space which is equipped with an inner product is also called an inner product space. When sometimes people say inner product space, the meaning is that simply this is a vector space and there is a inner product defined in this space. And this inner product obeys the properties of hermeticity. That is, it is equal to its transpose conjugate counterpart and linearly. Further, an inner product allows for the definition of a distance function in the state of space. So we have basically the same state, inner product psi should be greater than equal to 0. What does it mean? When it is 0, when its equality sign is considered, that means psi inner product itself is 0, basically says that the vector psi is also a non-vector, which we say as 0. This is the property of positive semi-finite of the inner product, and the length of the norm of a vector psi is nothing but to consider the norm of the vector psi, whose value should be psi inner product and square root. So what we see that the length of a vector is related to its inner product, right? Because right hand side is the inner product on which you have taken a square root. Another important concept of that of the basis. Most of the time we say, then in what basis we are defining the vector space. The basis is a set of vectors which is linearly independent and complete. That means if a vector space, I call it nu, not neutrino, but nu is the vector space, is spanned by a basis, say for example, a set of states phi I going from 1 to n, then any vector psi in U can be expressed as a linear combination of the basis, that is, vector psi is sum over I from I to n, phi I, which is another step, and here n is the number of vectors in the vector space nu. And completeness in this language implies that sum over state I and with graph phi multiplied by state phi, this should be equal to 1. Then it is what we call completeness. And this also implies that when the basis spanning the vector space is both linearly independent and complete, then the number of elements of the basis is equal to the dimension of the vector space. This you should understand. That is what I had kept at 9, n, small n, That's the dimension of the vector space, and the completeness and other things, as I said, tells you that this should be relation, they should. And now I'll define an operator which is represented by an outer product. Just keep a difference in the mind. What do I define an inner product? Now I'm going to say what is an outer product. So for example, if there are two vectors psi and phi, an operator is constructed as the so-called outer square, the bra psi and the cat phi, which form a simple matrix multiplication in the basis and can be seen to have the form of a matrix. This is basically the matrix representation I am using for an operator. So, okay, so you should have clearly conceptual difference between inner product and outer product. Inner product is by states, outer product gives us an operator. I hope I'm making myself clear to you. And the general definition of operator, you can write as it acts on a vector to produce another vector. So the operators will act on one vector to give you another vector. Okay? So for example, mathematically I can express this is the outer product of psi and phi. As I told, that's an operator. That operator is acting on another state chi to give you a state psi and the inner product of phi and chi. And of course, finally, this inner product is always a number, can be a complex number. So that complex number I have put at C. Many times we'll say a C number. A C number means it's a complex number. So you saw from here how an operator acting on a state gives another state sign. A special case about this operator acting on a vector is very interesting. This gives an eigenvalue equation of an operator which you are most familiar with. The Hamiltonian system, which is in quantum mechanics becomes an operator. It acts on a state psi and to produce you a number lambda on the same state. So this lambda here is called the eigenvalue of the operator A, and psi is a given vector. It's called the eigenvector. Two kinds of operators find very prominent use in quantum mechanics. One is Hermitian operators and the other is unitary operators. These two operators are useful developing most of the quantum system. An operator will call Hermitian if it is equal to its transpose conjugate. This is also known as the adjoint of the operator, and it's represented by a diverse sign. All of you are familiar with that. The adjoint of a unitary operator is its inverse. You know that U dagger becomes U inverse, then you can say U dagger equal to 1, which is same as U inverse is equal to 1. And the eigenvalues of the Hamiltonian operator are real. It should be actual for it is true for all Hermitian operator. I just told Hamiltonian operator, of course, which is Hermitian. And that's because you mainly use the Hamiltonian operator, but it's true for all Hermitian operators. They are real. This operator acting on some state produce a real value, and that's the reason it is a very important concept in quantum mechanics. The eigenvalues of unitary operator are complex with unit modulus. What we get? It would take the norm of that state, or well, that's what we call uh, uh, the can be related to physical operators, and unitary operators are basically used for the evolution of the states. If you have what do I mean by evolution of the state? If you define a state at time t equal to 0, you can use the unitary operators to evolve the state from this, which is at 0, to the state at a given time. Okay, so that's what I've written down there. State psi t is equal to an unitary operator which basically labels two things, time and time equal to 0, and that when acts on the state at time equal to 0 takes you to the state at time t. So let me say just what do I mean by unitary evolution, and that preserves the norm of the state. That means two states at same time, just we took the inner product. You can see that you can decompose the prior state psi t as unitary operators, and since I told that U dagger U is an identity operator, you can just insert this here, and that will take back the side. If U acting on brass state is taking you from time t equal to 0 to some time t, similarly the Hermitian, the unitary operators inverse, which I called U dagger, also takes the ket states psi at time psi at time t equal to 0 to psi at time t equal to t. This acting on this, so this is equal to John just because U dagger U is 1. That is basically the norm is same as psi 0 and psi 0. Okay, so even if we start with inner product of two states at time t, that will be same as the inner product of the state at time t equal to 0. Okay, so these are norm preserving. Another important transformation is similarity transformations, which you have used in many occasions in your quantum mechanics and field theory, or even mathematical methods of physics courses. So what does it do? Given an operator R and a unitary matrix U, so built from the eigenvalue of R, and the similarity transformation will be, which are written as some operator or matrix is equal to U dagger R U. So this D is the diagonal form of the matrix R. So I'm not saying anything new here, but I'm saying that given a matrix, forget about quantum, etc., you can do similarity transformation to bring the matrix to its diagonal form, which is easier to handle for many purposes. So in this particular case, we say the matrix D and matrix R are similar, and that is the name similarity transformation comes. So let's see now there are two operators A and B, and if by chance it happens that commutator AB, which I have defined as AB minus BA, not only I have defined, many people, some people had defined and we are using it. If we assume non-degeneracy, what basically means different eigenvectors corresponds to different eigenvalues. Please note here, different eigenvectors corresponds to different eigenvalues. And if that happens for A and B, we can measure it simultaneously. This is touching upon the measurement in quantum things, but this is the concept behind that. Okay? And a useful representation of an operator is its spectral representation. You might have heard, okay, but at least I had not heard till I passed MSc, the spectral representation of an energy. So this means that given an operator A, the spectral representation is given by A equal to I to n. Remember that n I have been using in the dimension of the vector space. And eigenvalue lambda I at this I and I outer product basically is an operator. Okay? So this lambda I going from n as I between 1 to n are the eigenvalues and eigenvectors of the operator A. Okay? Uh, Sorry, this is just from my note I had taken last night, photographs and putting it in a PDF file. So that's important. Now, another thing I would like you people to recall is various pictures we use in quantum mechanics. And that's because depending on the system you are working on, one of the picture becomes interesting. So we use basically three operators like Schrodinger picture, Heisenberg picture, and another one when there is interaction involved, we say interaction picture. Just recall that in Heisenberg picture, the time dependence is carried out by operators, while state vectors are time independent. I show some example from going to psi t, whose norm becomes same as psi 0. So, uh, in this particular Heisenberg picture, we will change the operator from one time to another time by performing some transformation, and then we will go from one time to another time, and this time dependence of operators keeps track of everything, so we can get away and not do anything evolution for the state vectors. Okay, so they are time independent. But in the Schrodinger picture, the thing is opposite. Here, the operator are time independent, and the state vectors are time dependent. The third one I told you, the interaction picture, this is some in between these two Schrodinger and Heisenberg pictures. They can be time dependent or not, depending on what we are doing. In the Heisenberg picture, the evolution of an operator, which I call O, and I've given there a superscript H, telling that it is Heisenberg picture. And in time t, this is given by the evolution, time evolution of that operator in the Heisenberg picture is given by exponential I by h cross ht. H is the Hamiltonian. Please distinguish between curly h and usual h we write. And the operator at time acting, this operator acting, these two, it was IHT, this is minus IHHT, acting on the operator in Heisenberg picture at time t equal to 0. So this is what we learn here, how in Heisenberg picture an operator that's evolved in time. Yeah, so I mentioned that distinguish between curly h and this. So now differentiation with respect to time, from here you can see that we will derive an equation which is IH cross del by del t, and the operator, since it is time dependent, you can act on this, and then what you will get is a commutator between the operator at time t with Hamiltonian. Okay? So you see from here, do you left hand side looks like that what we do in quantum mechanics, and the right hand side is an object, but this is another form of the operator evolution in time. So the state vectors in this picture don't evolve in time. It means if you take a state which are denoted alpha at given time t in the Heisenberg picture, this is same as the state alpha at time t equal to 0, and basically what we can say, since it is time independent, we just set the state alpha in Heisenberg picture. Okay, I hope you are going along with me and following the logic. Okay, so let's see then what happens in Schrodinger picture. In this case, again the operator O with superscript S is basically this operator in Schrodinger picture, and as I mentioned, this is same as the operator at Heisenberg picture at time t equal to 0, because the Schrodinger operator will not evolve. That's the reason I've taken that at time t equal to 0, that side. While the state I told you in the earlier picture, I take the same state alpha t, but now in Schrodinger picture, which is equal to e to the power minus I by h cross ht, h being again the Hamiltonian system, and it is acting on the state alpha at time t equal to 0, the state being again with Schrodinger picture, and now you can write down simply is equal to alpha. So you see that alpha at time t equal to 0, the state that in Schrodinger picture is same as the earlier state, which was not depending on time. It's same state alpha in Heisenberg picture. This is the way we equate a state in Schrodinger picture with a state with Heisenberg picture. Okay? So again, if we differentiate with respect to time, you will find the equation IH plus del by del t, and the state in Schrodinger picture which takes care of time, which will give you Hamiltonian acting on the state alpha t in Schrodinger picture. Okay, so here you see that it is more like E psi equal to H psi, which generally we follow. When we repeat H cross del by del t, H the Hamiltonian evolution operator. So we can show now that from the above, starting with state beta t and an operator with Schrodinger picture, which is acting on the state in Schrodinger picture, can give you state beta, and then you go from operator and act on that e to the power IH plus HT and e to the power minus IH plus HT on a state alpha which is in Heisenberg picture. And then it is easy to see that this is equal to the state beta, an operator in Heisenberg picture which carries time and which acts on a state alpha which is in Hilbert space. So starting from operators and states in Schrodinger picture, we can go over to an operator at a given time in Heisenberg picture and acting on alpha and beta. The transformation between the two pictures is mediated simply by our canonical transformation. And what does that mean? The transformation preserving the commutation relation, which is commutator between an operator A in Heisenberg picture and another operator in B in Heisenberg picture, giving another constant or C number as I told in Heisenberg picture. But we can also see that if you take the commutator between these two operators in Schrodinger picture, that will give you a different or the same thing. The C H superscript H and S is basically that C number we will get in two different pictures. And what does interaction picture do? As I told, this is an intermediate between the two, between the Schrodinger picture and the Heisenberg pictures. It is very suitable most of the time to system where the total Hamiltonian can be split up into two parts. One I will call the free Hamiltonian and the other I will call the interaction Hamiltonian. That the name actually interaction picture takes care of this. Whenever we can decompose the full Hamiltonian to a free Hamiltonian part H0 and an interacting Hamiltonian Hi. And in this picture, the operator evolve H. Now I put again I subscript to say that it is an interaction picture. And at a given time, you can start with the Schrodinger operator, which didn't have time dependence, but you can make this transformation, and that basically gives you the operator back in the interaction picture. No, and similarly, since it is intermediate between them, the state vector evolves as a state alpha at time t in interaction picture will just act this e to the minus IH cross H naught t and acting on the state alpha t in the Schrodinger picture. This is interaction picture, left hand side, right hand side, and operator, which is only the free Hamiltonian part, acts on the Schrodinger state. That's another relationship there. However, if you differentiate this, and you will find the IH cross del by del t on the interaction picture state alpha t, it will give you back the interacting Hamiltonian part, because we are not considering the whole Hamiltonian. We split it to three part and intraday part. Now you see that the time evolution in the interaction picture will need the interaction Hamiltonian in interaction picture acting on the state alpha t in the interaction picture. Okay, and we can also see that this operator IH cross del by del t acting an operator in the interaction picture at given time t is basically the commutator of the operator at time t in the interaction picture with the Hamiltonian, three part of the Hamiltonian. Okay, so this is all I told you, three different pictures, and in each picture, how the operator transforms or the evolution of the operator and the evolution of the state. But what we'll see in our purpose for studying open quantum systems, this is not enough. We have to consider some other operator, and represent them as matrices. And the operator is very important, which I'll just tell you in a minute. And this matrix is called as density matrix, density operator, and they are represented by matrix. So this is very useful in studying issues related to open quantum system. Let me now recapitulate some of the properties of the density operators, which many people try to avoid in learning or teaching in the classes at least up to MSc level. So let's consider the average of an operator, which I call M, in the Schrodinger picture. Where the state evolves with time, but not the operator. So we'll consider this state psi in Schrodinger picture at time t, and we can show that there exist operators average. So the average is taken as the operator in Schrodinger picture, where this does not evolve in time, but this is a element, matrix element of the operator, which in same time, but vectors are in Schrodinger picture. This we can rewrite as trace of the operator M in Schrodinger picture, and the outer product in Schrodinger picture psi st, that is the region. And this is the way we will take operator in Schrodinger picture, the average of an operator relating to, if those are matrices, how trace comes in, and how this outer product comes in. And in many cases, it is not possible to determine exactly the state psi in Schrodinger picture at a given time and to which the system belongs. The best one can do here is the find out probability, which I am denoting as P psi of the system being in the state, the Schrodinger picture psi s at given time t. So basically we are looking for, if you cannot determine psi st, what we should do is that we can try to find the probability P psi of the state being in the state of this. Then the operator average modifies to, instead of just saying average here, there are double average here, and that the double average I put because one of the average you will take with the probability of finding psi. So with this, then it becomes simply trace of the matrix in Schrodinger picture M and the density matrix in Schrodinger picture at given time. Okay. Sometimes we refer to the double average. But this density matrix or operator sometimes becomes odd to say the operator or matrix, because when it is matrix, it is the predecessor of that operator. Okay. This is given by sum over the probability of finding that psi and the outer product. You can see that since there is an outer product here, this is an operator. Okay, so the density matrix is an operator, and of course we should have the constraint sum over the probability P psi over all psi should be equal to 1. Then you can say that yes, it's a probability of finding the state psi in that. This density matrix also satisfies two interesting properties. The trace of the density operator or matrix, that has to be 1, and trace of square of this density operator, square means basically twice you are operating, should be less than or equal to, after taking over the trace, less than equal to 1. And in this, when it is exactly equal to 1, then we say this is a pure state. So it's a pure state for the density matrix operator. And when it is less than 1, this is a mixed state. So how to define pure state and mixed states, how to distinguish them becomes very clear in this description via the density matrix. I want you to remember that somewhere when you are able to write down the density operator or matrix, first thing you have to check that there's a density matrix operator, if trace is 1, and with a square of the operator, then you have to find whether it is a pure state or mixed state. Sometimes people say entangled state, etc. I will not go in these things to give you too many names, but this is where we can see. Now, if we use the Schrodinger equation, IH cross variability of psi equal to Hamiltonian Arcadian psi, we can also show that this density operator rho satisfies this time evolution of the density is nothing but commutator between Hamiltonian and the density matrix operator. Okay? So this is sometimes, this particular equation is or it's called the Schrodinger von Neumann equation. Okay? If it was only H acting on rho, then we would have told that it is a Schrodinger equation, but having in this commutator way, it's also known as von Neumann equation. I'd like to now give one example. Consider a two-level system representing a qubit, which I told, with the Hamiltonian given in Schrodinger picture, which is h cross omega by 2, and the third Pauli matrix, which is the 1, 0, 0, minus 1. And if we try to consider now as the system eigenbasis, which are taken written as vector j and m. Remember, they are now depended by two different indices, j and m. So this is sometimes called Wagner-Dickey states, this particular way of representing. Then the eigenvalue equation of the Hamiltonian and Schrodinger picture is basically take that Hamiltonian, act on the state Jm, what you will find is h cross omega and a small m is the eigenvalue acting on Jm. And this quantity altogether, you can write that energy Jm acting on Jm, because you will start from the Hamiltonian, what we should get is an eigenvalue. And this small m varies from minus j to plus j. Okay, so there are two j plus 1 equations involving this. So to consider the initial state to be some state psi at 0 and write it, because as I told you, it's a two-level system and we are considering a qubit. So the eigen state is cos theta 0 by 2 acting on the vector O or 0, and the e to the power I phi 0 sine of theta 0 by 2 with the state 1. This represents the state of a qubit and the theta 0 and phi 0 being the polar and azimuthal angles respectively. This is in your quantum mechanics, you have also log, angular momentum, etc. So this is that particular way of putting this thing down. And the time evolved density matrix now takes exactly this matrix that's at a given time, and we can write all these things acting on this matrix with theta 0 and phi 0, these two angular momentum and azimuthal angles, which are H states. No, it's already this density. This is an operator representation of this matrix. I will give you a simple assignment to check if the above represents a pure or a mixed state. Remember, I told them that the density matrix trace of that should be always equal to 1. See, test this. If the trace is 1, and we have considered this already, net. Let's say that. But we have to also look at take the square of that matrix and take the trace which is coming out to be 0 or less than 1. That's what I told you. Then they will be pure state. Do this for yourself. Now let's find a convenient representation of a single field mode. From matrix, sometimes I put in field mode because the fields actually gives you excitation or the linear combination of various operators. And just like harmonic oscillator, I have chosen now the single mode. There is only one mode of the number operator here, which will be acting when this acts on this step, will give you the eigenvalues of a dagger A along with this. So this when it is in thermal equilibrium. So what it means is that I can take an harmonic oscillator and connect it to the environmental heat bath, but the two systems are in thermal equilibrium. That means they are in the same temperature. Okay? We'll see the same situation when the bath has a different temperature and this harmonic oscillator had a different temperature. And that is where we cannot say it's a closed system because both have a different temperature. But in the closed case, when we say about temperature, etc., always we consider a closed system. Okay? But let me talk a line which had kept me puzzled for quite some time when I was doing cosmology. In that, the universe is expanding. Early universe or even now. So the universe is expanding. There is change in temperature. But then, so it is change in whatever we consider, whether it is inflation or this and that, it's all happening in the background of a temperature. So in principle, we should always solve this issue, evolution of our inverse, in a thermal non-equilibrium, unless the rate of expansion of the inverse is much, much slower than the time scale of the system you want to study. So that we can say that it is neglected. If it is. If it is not, then we are going in the wrong path. We have to discuss the system in thermal non-equilibrium, and the thermal non-equilibrium is a subject of itself. Most of the time, the people who work in condensed physics or statistical physics, or they go over to the quantum regime, this part we neglect. Okay? So that's a side comment I made. Now let's find a convenient representation of this field mode. I've given the Hamiltonian and I said it's in thermal equilibrium. We can write the density operator as simply equal to e to the power minus beta h by z. And that z is nothing but you can see from here raised over e to the power minus beta SW and the operator itself. So here I put the representation of or taking trace over all the operators, and in a different language in path integral you will see it is sum over all states, and beta is your usual definition 1 by kb by T, for T the temperature and kb is the Boltzmann constant. Okay? And the stress you can take over it and find the result to be 1 by y sine hyperbolic of beta h cross omega by 2. Also, if you use the completeness of basis, which is composed of the eigenvalues, which are talking about the harmonic oscillator issue as the states with n number of particles. That is like n. And it should also satisfy sum over all completeness theorem is 1. We can see that e to the power minus beta h by inserting the completeness issue here will simply come over to the density matrix sum over n. Then these are numbers 1 minus e to the power minus beta h cross omega, and another number there which will be acting, which is this side left hand side is an operator. We have also operator there, and sum over n is that you have taken all states the given particle number n. Okay, and I will also use this later on. There is another identity involving the density matrix, which I call a squeezed thermal state. And the density matrix there has a script SQ, meaning that it is squeezed, and TH between that in thermal. So this operator is simply defined as the thermal density matrix and sandwiched between two operators S and S diagonal, which depend on R and phi. So the rho TH basically the same thing in the thermal bath. We just defined or derived that now. And this operator S, which depends on R and phi, is the squeezing operator, and one finds that the squeezing operator is given by exponential of R times A operator square. There again A operator square means I'm operating the annihilation operator of the harmonic oscillator twice. And fh e to the power minus I to phi. Similarly, minus a Dagger square by 2 and e to the power I to phi. Okay? So again, r and phi are now called the amplitude and phase of squeezing. So it is just like what we mean by the squeezing. If you take something in squeeze, you can see that it will come to a vibrating state, and it will, the amplitude of that vibration is the amplitude I'm talking about, and the state can be always written with a phase. So that I've used the phase as this. So this identity, or we are looking for an identity which will be used later, is the expression, the trace over this row I define with another operator d, whose x minus x prime, and you can simplify this, which I've done there, with this d operator, which I call the displacement operator, is given by exponential of x and English for a minus x star creation operator a diagram. So this is displacement. You can check that, you will find this way. And I would like you to prove an identity operator S and acting on operator D, and then this was S diagonal and this is S. You will find that the operator D takes the function of x cos hyperbolic r plus x star sin hyperbolic r, and this term has a phase e per I2 pi. Okay, please do this work and then I try to complete the derivation, meaning that then you'll understand what's going on. Okay, how much time I have now? I started at 10:30, right? 11, so it should go to 11. It should go to 12. Okay. So there is, I'll take 5 more minutes and leave you for the discussion. Okay, maybe tomorrow I will start with the concept of partition function and then go, as I told in the beginning, even if I don't reach the point of describing open quantum system systematically, the basics should be understood, and I should not say that oh, this can happen, that can happen. That I will have to do that. I will stop here, and tomorrow I will start from here. How do I write partition functions? Okay, which both classical as well as quantum. Thank you. Now I'm open to discussion, questions.
Thank you, sir. So now the floor is open for questions and queries